Hi guys, Harry here. Welcome to Scrap Science. Today we're going to be attempting the quite difficult task of producing permanganates, or potassium permanganate, using manganese metal, which I bought from eBay, and potassium carbonate. Now, making permanganates is a pretty tricky business, at least from an amateur's perspective. There are a few ways to do it, but most of them involve some pretty tricky oxidisers or incredibly high heat, and they often result in some pretty poor quality permanganate product, or it's very tricky to separate out. And in most of these methods, the yield is pretty terrible most of the time. Now, given this difficulty, we were given a suggestion in the YouTube comments of a previous video by a user, Anti, who was suggesting the process outlined in this paper that I have here. It's a very, very old paper from September 1921, so that's 99 years ago from the time that I'm making this video. Is the electrolytic production of sodium and potassium permanganates from ferromanganese. Now, this method in this paper seems actually very doable, especially for this channel where electrolysis is our thing. Basically, all it describes is the use of a manganese metal anode in a potassium carbonate solution as an electrolyte with an electrolytic separator, and performing electrolysis on that setup will apparently generate a high yield of potassium permanganate in the anode chamber, which is what we're going to have a go at today. Now, the paper might seem a little bit dubious at this stage. I mean, it was written a very long time ago. However, despite how old the paper is and the fact that this method hasn't really been referenced in any literature since, at least that I've been able to find, they do go into a lot of detail, finding the optimal conditions for the reaction to work. I think they did close to 180 tests overall, and the results were replicated by a Science Madness Forum member not too long ago. So as for this method actually working, it's looking pretty good, I think. Now, I won't bore you with the details of the paper. It's quite long, and you can have a look in your own time if you care. But basically, they summarize it at the end. The optimal conditions for making permanganates is to use between 15 and 30% potassium carbonate solution as the anolyte and the catholyte. This apparently leads to the highest efficiency, and the anode doesn't appear to passivate under those conditions, so that's good. That's what we're going to do. And then also the proportion of manganese content in the anode itself, as the manganese content increases, then the current efficiency also increases. That was a problem for them back in 1921, when it was probably quite a bit more difficult to get a hold of 100% pure manganese. They had to use ferromanganese, which had quite a bit of iron impurity. But what we're going to be working with today is some pure manganese metal, so I think it should work out quite well. Now, you might remember a few months ago I made a video in which we synthesized manganese metal from manganese sulfate. I have that sample right here. This is the manganese metal we made. So you might wonder why I bought some from eBay, where we had the capability of making some ourselves. And the reason for that is I did actually try making a manganese electrode, or a graphite substrate manganese electrode, and it worked relatively well. This is kind of crumbling apart after quite an extended period of storage, but I did try this out. You can see what I've put together here is just a graphite rod with some manganese metal that I plated onto the end here. Anyway, I tried the process with this electrode, and what seemed to happen was the junction, or the connection between the carbon and the manganese itself, seemed to passivate, and I really wasn't able to get any kind of current flowing actually through the manganese producing our permanganate. So basically what I wanted to do with the graphite substrate and the manganese electrode really isn't ideal for the process that we're trying today. In the future, what I'm going to try is, instead of using graphite as a substrate, I've got some titanium here. Hopefully this might work much better in order to make a proper connection to manganese. But for now, because we really want it to work, I just bought some big chunks of manganese off eBay. You can see, I'll take it out in a sec so you can see it properly. Hopefully, seeing as this is just the pure metal and we can just make an electrical connection straight onto that, we should not have any problems with the connection to any substrate. So without further ado, we will set it up. I have here some 25% potassium carbonate solution, which I made up previously, and we have here our electrolytic cell that we're going to use with our electrolytic separator and a carbon rod to use as the cathode, the manganese as the anode, and I think that's it. So we'll put it together, get it connected up, and see if we can make some permanganate. Alrighty, we have all of the electric bits set up, and the only thing left to do is connect up our anode, our manganese anode, and dip it into our solution, which we have filled with our 25% potassium carbonate solution, and hopefully we will start generating permanganates straight away. So I'll grab a piece of the manganese that I got from eBay. You can see it here, it's quite shiny in some places. So we'll connect this up, we'll go like that and dip it in. You can watch the current meter on the right hand side there. You can see we are actually electrolyzing through the manganese, so I'll just put that straight down there. So basically you can see we're getting about 1/4 of an amp at a bit over 9 volts, which is about what we'd expect, I guess. You can see down in the solution, it's a little bit tricky to see because the lighting is so bad, but that looks like a bit of pink coming off the anode there, if the camera would focus, which might just be our permanganate that we want to be generating. I'll leave this for a few minutes and we'll come back and see if we have generated any pink or purple coloration in the anode chamber. 5 minutes into electrolysis and the results are very, very promising. It's a little bit tricky to see in there. I might try to turn on the light on my phone if I can figure out how to do that. There we are. So you can see, if we have a look in there, that solution is very pink at the moment, which can really only be attributed to permanganate formation. Now we can definitely tell that it's not just manganese ions going into the solution, manganese 2+. You can see this is a solution of manganese sulfate, which is kind of very, very faintly pink, but this is a very, very concentrated solution of manganese sulfate. So if we were making manganese 2+ in solution, we'd expect to see almost no coloration at all. Based on the fact that this is really almost purple now, it must be potassium permanganate, which is very exciting. So here we are, 15 to 20 minutes from when we started. You can see the voltage has decreased, and you can see that that coloration is distinctly purple now. We have quite a bit of permanganate that we've generated so far. You can see a bit of a side product of oxygen being generated on the anode there, but that seems to be going very, very nicely. There's no manganese dioxide forming on the electrode, which is kind of surprising to me, but it's a good thing, I guess. We have our hydrogen being generated on the cathode, and everything is going very, very smoothly. Now this is around the time where I would normally stop and explain the chemistry going on here, but there's really not much to it that I understand, to be honest. Obviously there's oxidation of the manganese metal going on, oxidizing the metal to the permanganate ion, but aside from that I really don't understand why we're not generating any manganese dioxide or any manganese 2+. And the paper certainly doesn't give much information on that either. So we'll just have to be content with the fact that, and we have hydrogen being generated on the cathode, we've got permanganate being generated on the anode, and because we have our clay pot electrolytic separator, the permanganate that's being generated on the anode does not flow over to the cathode just to be reduced once again to maybe manganese dioxide or manganese 2+. So all I think that's really left to do is to leave this running for an extended period of time, thinking 24 hours at least, see how much permanganate we can get in that time, and we'll get back to you and try to extract out our potassium permanganate product. Alrighty, so we are back the next morning. The cell has been running for about 18 hours, and it seems to have been going very well. I mean, the voltage has risen a tiny little bit. We're up to 5.3 volts or so, but that 0.25 amps that we've had running through the cell seems to be doing perfectly fine. If we get a closer look, you can see that we have an incredibly intense purple colour in our anode chamber, as we'd expect. Now we can't even see the little white dot on the bottom of the clay pot, so that's a very good sign that we're getting at least a reasonable concentration of potassium permanganate. I'm not sure what those little floaty bits are. It'd be really nice if those were potassium permanganate crystals, but I do doubt it. I reckon that's just something that came off the manganese metal electrode. The only other thing I have to say about the process at this stage is the fact that it is quite slow going. Yesterday I kept a pretty close watch on the cell, and it took quite a while before the solution became opaque, and I guess that makes sense because, well, really, to convert manganese metal into permanganate, you need to take away 7 electrons, which is quite a bit of current, or charge, I should say, that we have to actually push through the cell in order to generate a reasonable quantity of permanganate. So I'm thinking maybe I'll leave this cell going for at least 48 hours. So maybe we'll leave it running till tomorrow and see where we're at then. If we have a look at the anode, you can see we really haven't dissolved very much of it. So really there's a lot more permanganate that we could be making, and I really want to get as much as we can out of this cell. Just before we skip ahead, in order to make a really crude estimate of the concentration of our permanganate, I've taken out 1 milliliter of our permanganate solution here, and I'm going to dilute it by a factor of 100. So if we drop this into the beaker here, you can see the amazing ability of the potassium permanganate to colour solutions. I believe it's one of the most coloured compounds that exists. Anyway, based on how coloured this solution is, we can make a really crude estimate of the concentration. By my estimates, the solution in this beaker is around about 15 milligrams per litre worth of potassium permanganate, which isn't very much, but consider that we diluted by a factor of 100, right? In our original solution, in the actual cell, we have a concentration of around about 1.5 grams per litre, which is still a fair way off any kind of high concentration that we might want, such that it's easy to separate out. I do think we are well on our way to generating significant quantities of potassium permanganate. So we'll leave it running and get back tomorrow. Alright, it's another 24 hours since our last update, and I just have a couple of things to say. In that time, I have turned the current up all the way to 0.65 amps, just because 0.25 amps seemed exceptionally slow at dissolving away our manganese anode. That increase of current seems to not really affect the running of the cell. The cathode is doing fine. I replaced the graphite cathode just with a wire, seeing as the graphite wasn't getting a very good surface area. The only other thing I wanted to mention is the fact that leaving this running for an extended period of time, we did see the current taper off considerably. I think it dropped to around about 30 milliamps, and what I think that was due to was the fact that during our electrolysis, all of the potassium ions in the anode chamber had migrated to the cathode chamber, and so what we'd started generating in the anode chamber is permanganic acid. That's what I'm guessing, and that really kind of shut down how the cell was working. So the solution I found was to simply just pipette around 15 milliliters of our catholyte solution, which is where all our potassium ions are in order to make our potassium permanganate. We want to pipette 15 milliliters or so of our potassium carbonate, potassium hydroxide mixture that we've generated in the cathode chamber, and just transfer that over into the anode chamber, and everything seems to be running smoothly once again. If the current tapers off at all in the future, I'll just repeat that, maybe transfer about 10 milliliters or so back into the anode chamber. Anyway, everything seems to be going smoothly, so maybe I'll even turn up the current a little bit later, but for now I think we'll take out 1 milliliter, dilute it by a factor of 100, and see if we have made any progress since our last update. And we'll see how concentrated that looks. So by my estimates, which are again very, very rough estimate, this solution would be on the order of around 50 milligrams per litre worth of potassium permanganate. So considering that this is diluted by a factor of 100 from our original analyte, we should have in the actual cell a concentration of about 5 grams per litre, which is nowhere near saturation yet as far as potassium permanganate goes, but we are developing a pretty good concentration. What I think I'll do is, considering how well the cell is running currently, I think I'll turn up the current as high as I can, and we'll leave the cell running for as long as we can and see just how much potassium permanganate we can generate. So there we are, I've turned the current up to 0.8 amps. We have put in a second chunk of manganese metal, put some more surface area for the cathode just to keep that voltage nice and low. And I've also added this thermometer here in order to monitor the temperature, because according to the paper, if the temperature rises much higher than around 30 degrees, then things start to go wrong. But either way, I'll leave this going, provided there are no problems that I run into for the next maybe a whole nother 48 hours, and we'll see where we're at then. Alrighty, we are now 100 hours into running the cell, and I think honestly it's about time to stop. I've really struggled to keep the current up, even by transferring some of the potassium hydroxide, potassium carbonate solution from the cathode chamber into the anode chamber. Really doesn't keep the current very high at this stage anymore. It's been going really well so far, but I think it's about time to stop. The catholyte has become kind of murky, and the analyte is looking like very concentrated potassium permanganate, or relatively concentrated at least. So I think what we'll do is we'll take out all of the potassium permanganate from the anode chamber, maybe wash off the electrodes and everything, and I don't really have time today, but tomorrow we'll get around to extracting and maybe crystallizing out, if we can, the potassium permanganate that we've made. Okay, here we are the next day, and we are ready to measure and extract our potassium permanganate that we've made. You can see this is the solution that was our analyte from the cell. You can see it's very, very purple. It's a very nice color, to the point where it is pretty much completely opaque when you actually look through the solution, so that's very good. Anyway, what I think we'll do first is actually properly measure the concentration of the permanganate that we've generated, because separating it out is going to be pretty difficult, recrystallizing it anyway. So we kind of want to know exactly how much we do actually have in this solution, regardless of how much we're going to extract later on. So the way to do that is to titrate the solution. So what I have prepared earlier, we'll put this aside for now, is a 5 times diluted solution of our potassium permanganate. And I recently bought a burette, which is exactly what we need to do a semi-accurate titration of our potassium permanganate. What I'm going to do is titrate this against a standard solution of sodium bisulfite, which will reduce the permanganate content to manganese 2+ in acidic conditions, and from that we will be able to work out the concentration of our potassium permanganate in our original beaker here. Alrighty, so we're all set up for a titration. We have the potassium permanganate in the burette here, and we have our sodium bisulfite solution, aliquot, acidified with sulfuric acid down the bottom here. So we start adding the potassium permanganate to the aliquot very slowly. That looks like the end point to me. Time to do some maths. Alrighty, having done the maths, we arrive at the result that the 50 or so milliliters of potassium permanganate solution that we've generated in our electrolytic cell is around about 0.21 molar concentration, or 33 grams per litre, which is way better than I was actually expecting from a process like this. I mean, we weren't trying very hard to be particularly efficient with our electrolysis, and honestly that kind of concentration is almost approaching saturation for potassium permanganate. I think it's over saturation if we were to cool this down to 0 degrees Celsius. So we might, if we had to put this in the freezer, we might see some potassium permanganate crystals crystallizing out. What I think I'm going to do to extract potassium permanganate crystals, if we can do it, is first of all we'll filter this and then maybe boil it down to half its volume, and then see if we can crystallize anything out upon cooling. Alrighty, time skip to the future. I have spent the last 2 days trying to crystallize out some of this potassium permanganate, and I have absolutely failed. I'm giving up now. I tried boiling it down and then cooling it down to try to crystallize some of the stuff out. That didn't work. It just gave some sludgy stuff along with some tiny green crystals, which I assume were manganate crystals. Anyway, I tried that again. Again, it didn't work. Then I tried acidifying the solution with some sodium bicarbonate, which seemed to make everything go a little bit better, but I never got any big retrievable crystals of potassium permanganate out of solution. The best I got after boiling down the solution, I got these semi-purple kind of dust, which I would assume is completely impure, with a whole bunch of potassium hydroxide, potassium carbonate, sodium carbonate, and whatever else is in there, maybe manganese dioxide. Who knows? But basically it was just far too difficult for me to crystallize out the potassium permanganate stuff, and I'm pretty sure in drying out these all of this powder, I'm pretty sure I decomposed most of the permanganate that we made in the electrolysis cell. So that's very disappointing. Really, I would attribute this failure to my poor ability to recrystallize compounds. I'm really bad at it, and this is basically why we didn't get any pure yield. I'm sure someone who's better at me at chemistry would be able to actually separate some of the potassium permanganate out as pure crystals. So there are a few things that we weren't able to do at the end of this synthesis. We weren't able to separate out any solid permanganate, any usable solid permanganate. We weren't able to separate out any pure permanganate. However, there are a few things that we were able to do with this synthesis. We were able to generate a very high concentration of potassium permanganate, around about 0.2 molar. We were able to generate quite a large quantity of permanganate. We made about 1.5 grams with our electrolytic cell. So I'd overall say that this synthesis is somewhat of a success. I'm confident that if we perform the reaction on a larger scale, so we made like a bigger cell with a larger manganese anode and pumped more current through it and generated more potassium permanganate, we'd be able to separate out our potassium permanganate as we would have liked to today. So this method with this paper is actually really good. It doesn't require the super high temperatures that most potassium permanganate syntheses require, which is a big plus. And the solution that you get out of the anode chamber from the electrolytic cell is pretty much usable itself as a potassium permanganate solution, seeing as it's really high in concentration. That is, provided that whatever you're using the potassium permanganate for, it doesn't matter if your potassium permanganate is contaminated with maybe potassium hydroxide or potassium carbonate. The major problem with this synthesis comes from the fact that the main starting material, manganese metal, is really difficult to come by. It's really not an off-the-shelf thing that you'll be able to get anywhere in the world. Hence why we tried our best to make a manganese electrode from manganese sulfate, which is a much more available chemical. It is something I will revisit. As I said before, we'll try using a titanium substrate rather than a graphite substrate to make a manganese electrode, and hopefully once we revisit this, we'll do it on a larger scale and see if we can get actual potassium permanganate crystals out. But overall, I do still think this was a success. Thank you, Auntie, for the suggestion. We were able to make permanganate, but I just couldn't pull off the final step of crystallizing it out. So with that, see you later.